Previously, we modeled the motion of a mass attached to a spring, assuming that there was no frictional force on that mass or no air resistance. So now I would like to update that model by considering a mass m attached to a spring with spring constant k, but I want to add that there's a frictional force, and that frictional force is proportional to velocity. So what we have here is that m, mass, times acceleration, which is d squared x dt squared, is going to equal minus k times x, because Hooke's law says that the force exerted by the spring is proportional to the displacement, and that constant is negative. But also there's going to be an opposing frictional force. So that would be minus, I'll use the constant b, times dx dt, because that frictional force is proportional to velocity. Now, we can rearrange this equation so that it's actually m second derivative x with respect to t squared plus b dx dt plus k times x is equal to 0. And what we have is a little bit more general second order linear differential equation that has constant coefficients. Essentially, previously we did not have friction, so that term was missing, but now we're going to add it back in. So to solve this second order differential equation, I want to proceed like we did with the previous equation. And what we did was we looked for a starting point, an initial guess, and that guess was that our solution, x of t, was equal to e to a constant lambda times t. And that guess is still valid because what we're saying is that the second derivative of this function and the first derivative of this function and the function itself, if we add up a linear combination of those, we should get 0. So each one of these, the first and second derivatives, needs to look like the function itself. And e to the lambda t has that property. So the derivative of x of t is x prime of t, or lambda e to the lambda t. And then the second derivative is x double prime of t, which is equal to lambda squared e to the lambda t. So we want to substitute our x of t back into the differential equation so that we get m lambda squared e to the lambda t plus b lambda e to the lambda t, that's substituting for the first derivative, plus k times x, which is e to the lambda t, is equal to 0. And then what we're going to do is factor out the e to the lambda t so that m lambda squared plus b lambda plus k, say, times e to the lambda t is equal to 0. Or another way to write that is just that m lambda squared plus b lambda plus k must equal 0. Now, this has a name. This is actually called the characteristic polynomial of this equation. And the idea is that if we solve for lambda, then we know the powers or the constants that need to go into our solutions, e to the lambda t. That characteristic polynomial, that sounds familiar. It sounds like a term that we might have heard from another math course. And the answer is that we have heard that term in another math course. And it seems a little odd to be using the same term in for a concept that seems quite different. So maybe we'll just have to see if later on in this course I can reveal why it makes sense to use the term characteristic polynomial. For now, let's just find the roots of this characteristic polynomial. The equation is m lambda squared plus b lambda plus k equals 0. So we can use the quadratic formula to say that lambda is equal to minus b plus or minus the square root of b squared minus 4mk all over 2m. And sometimes we're going to find it is helpful to write this as minus b over 2m plus or minus, and then I would like to divide everything inside the radical by 2m. But if I move it inside the radical, that's going to be a 4m squared. So this is b squared over 4m squared minus k over m. So the characteristic polynomial has two roots, and so that's going to give us two solutions, e to the lambda plus t and e to the lambda minus t. But because we're dealing with that square root, there are going to be three different cases of what kind of behavior might occur. We could have the simple case that b squared minus 4mk is bigger than 0, in which case both roots are going to be real. So we're going to have two real distinct roots. Now it could be that b squared minus 4mk is less than 0. Now I'm taking the square root of a negative number. That means I could end up with complex roots. And then finally, I could have that b squared minus 4mk could equal 0, in which case the term in the square root is 0, and so I'm going to end up with one root, or repeated roots. So we would like to examine all three of these cases. Okay, our first case is real distinct roots. So we have two linearly independent solutions in this case. They are x1 of t equals e to the what I'll call lambda plus t, and x2 of t, which I'll call e to the lambda minus t. And so that gives us a general solution, and we'll call that general solution is going to be c1 e to the lambda plus t plus c2 e to the lambda minus t. Lambda plus and lambda minus are given by that formula above. Well, what is going to be the behavior of this system? Now, a lot of this depends on what the constants b, m, and k are. Let's for a moment assume that b, m, and k are all positive. That is the case when we're looking at a system that is a mass spring system with a frictional force. M stands for mass, and then I've given direction to the constants b and k using those negative signs. So we have m, b, and k are all positive. Well, if m, b, and k are all positive, our question is what about lambda plus and lambda minus? Are those all going to be positive or negative? or maybe one's going to be positive, one's going to be negative. Let's examine this term here. We have negative b over 2m, and then we have a square root, and notice that we have that term squared, b squared over 4m squared. And then we're going to subtract k over m. Well, the magnitude of the term in the square root is going to be smaller than the minus b over 2m on the outside. What's inside the square root is necessarily going to be smaller, and that's because the term inside the square root is the term outside the square root squared minus something that's positive. So what's inside the square root is going to be smaller. Well, that tells me that lambda plus, when I take the negative term and then I add the plus to it, I'm going to add something that's smaller. So lambda plus is necessarily going to be negative. So I can say that with these real distinct roots here, if we're dealing with a mass spring system, I can say that lambda plus is going to be negative. But looking back, I can also see that lambda minus is going to be negative, because lambda minus is the negative b over 2m minus the square root. And so everything there is negative. So I'm going to have that lambda minus is also going to be negative. So if I want to sketch the solution, then what will happen is that I will start at the initial position, we'll call it x0, and then I have, looking back up here, exponential decay, because e to the lambda plus t is got a negative lambda, and then e to the lambda minus t has a negative lambda. So they both have exponential decay. And so I will have this slow exponential decay over time. So this is time, and that is the distance x. And I say that it's slow because I'm anticipating that this term here, while less than this term here, is still going to be close to the value of that term. And so one of those lambdas, lambda plus, is going to be pretty close to 0. So that's going to be a slow decay. In this case, we call this an overdamped oscillator. Now, you'll probably think it's weird that I'm saying it's an oscillator. I don't see anything oscillating, but nonetheless, that's what it's called, and it'll become more apparent why it's called an overdamped oscillator after we look at the next example. What I'd like to think of with this example is you could think of a really a tough spring, so that if you pulled the mass on the spring and let go, it would slowly push back into position. But that example doesn't quite work in this scenario for me. What I like to think of is a door. Imagine you have a door that has some sort of shock absorber on it, something to make it close slowly, so that when you open the door and release it, that door slowly moves back into position. That is what I think of when I think of an overdamped oscillator, a door that slowly moves back into position. Okay, let's look at what happens in the scenario where we have complex roots. Okay, in this case, I'm going to think about my lambda plus and minus as being minus b over 2m, because that's the real part, plus or minus I times some number, we'll call it omega. Omega is essentially the negative of everything that's in the square root. Well, what happens in this case? Well, we're going to get two solutions. I'm going to call those two solutions x plus and x minus. And x plus is going to be e to the minus b over 2m plus I times omega times t. That's going to be e to the minus b over 2m t, e to the I omega t. And then we can write this out as e to the minus b over 2m t times cosine omega t plus I sine omega t. Again, maybe I haven't made this clear. Omega is going to be the square root of k over m minus b squared over 4m squared. So it's the negative of what was in the square root. Okay, well, I'm going to call that x plus. X minus the other root, okay, when lambda is negative, is going to be e to the minus b over 2m minus I omega times t. So that's going to be e to the minus b over 2m t, e to the minus I omega t. That's e to the minus b over 2m t times cosine of omega t minus I sine of omega t. Okay, so now we have two solutions. These solutions are linearly independent. Okay, it's not easy to see here, but they are actually linearly independent. What I want to do is look at linear combinations of these two solutions, because it's bothersome to me that this is a real oscillation or a real mass on a spring system that has some sort of damping to it. And the solutions that I got have complex parts that have no physical representation. So I'm going to let x1 be x plus x minus over 2. And in doing so, the cosines add together, and then I divide by 2, and I get e to the minus b over 2m t cosine of omega t. And the signs add together, and you get 0. So what I'm left with is just one real solution. x2 is going to be x plus minus x minus over 2I. So that when I subtract these two solutions, the cosines cancel, and what I'm left with is e to the minus b over 2m t sine of omega t. And then the 2 and the I cancel with the 2I in the denominator. And so what I have here are two solutions. These two solutions are linearly independent. You can show that using the Wronskian. So these are linearly independent using the Wronskian. So I have two of them. They're linearly independent using the Wronskian, so therefore they span. And so these are going to be my two solutions. They are going to be e to the minus b over 2m t cosine omega t. And then they're going to be e to the minus b over 2m t sine of omega t. And so the general solution is going to look like C1 times cosine of omega t plus C2 times sine of omega t. And then I'm going to go ahead and factor the e to the minus b over 2mt out. So let's look at what this solution might look like. So what I have here is a C1 cosine of omega t plus C2 sine of omega t. And that we know is going to just be an oscillation with a frequency of omega. But I have this e to the negative b over 2mt. This we can think of as being like the amplitude. Now I'm going to assume again that all my constants are positive, so that's a decaying amplitude. So what I'll do is I will plot that curve. Maybe that'll be x0. So I'll plot that curve, that decaying amplitude, like that. And then I'm also going to plot it on the negative side. So this is negative the amplitude, negative e to the minus b over 2mt. And then what I have is an oscillation whose amplitude is decaying. So it'll look something like this. So I have an oscillation that decays to 0. This is actually called an underdamped oscillator. Now you can see why there's an oscillation. So what's happening here is that the friction is not very large. And so our mass, if we were to pull on that mass and then release it, we would see the mass oscillate back and forth. And then the friction coefficient would take over and the oscillation would decay in amplitude over time until we get to 0. So this underdamped oscillator, a way to think about what it is imagine that you have a saloon door. Okay, so you're going to take a door, you're going to open it to, say, some saloon. And that door, if you release it, it's allowed to flap back and forth. So it's allowed to move through the door jamb, essentially. Okay, so you're going to open that door, and then you're going to release it, and you can imagine that it's going to oscillate back and forth, and eventually it'll settle down and stop moving. And that is a good example of an underdamped oscillator. I just want to mention, going back, something I didn't mention here is when I have these two linearly independent solutions for my real distinct roots, that as long as lambda plus and lambda minus are not equal, okay, here we can say that the Wronskian is not 0. You can actually show that yourself, and you probably did in a homework problem. Just like I had here with these two solutions, okay, that the Wronskian is not 0. They're linearly independent.